Respected Ujjwal Saikia sir, today I, Mohammad Ayub Khan, along with my presentation partner, INDRIM BORDOLOI, are going to give a presentation on a topic of mathematical expectation.
Mathematical expectations, also known as the expected value, which is the summation of all possible values from a random variable. It is also known as the product of the probability of an event occurring, denoted by Px, and the value corresponding with the actually observed occurrence of the event. For a random variable, expected value is a useful property. Ex is the expected value and can be computed by the summation of the overall distinct values, that is the random variable. The mathematical expectations is denoted by the formula Ex equal to summation x1 p1 comma x2 p2 to xn pn, where x is the random variable with the probability function fx, p is the probability of the occurrence, and n is the number of all possible values. The mathematical expectations of an indicator variable can be 0 if there is no occurrence of an event A, and the mathematical expectation of an indicator variable can be 1 if there is an occurrence of an event A. Properties of expectation. Number 1. If x and y are the two variables, then the mathematical expectations of the sum of the two variables is equal to the sum of the mathematical expectation of x and the mathematical expectation of y, or ex plus y equal to ex plus ey. And number 2, the mathematical expectation of the product of the two random variables will be the product of the mathematical expectation of those two variables, but the condition is that the two variables are independent in nature. In other words, the mathematical expectations of the product of the n number of independent random variables is equal to the product of the mathematical expectation of the n independent random variables, or exy equal to exey. The number 3, the mathematical expectation of the sum of a constant and a function of a random variable is equal to the sum of the constant and the mathematical expectations of the function of the random variable, or a plus fx equal to a plus e fx, where a is a constant and fx is a function. And number 4, the mathematical expectation of the sum of product between a constant and function of a random variable and the other constant is equal to the sum of the product of the constant and the mathematical expectation of the function of that random variable and the other constant, or eax plus b equal to aex plus b, where a and b are constants. And number 5, the mathematical expectations of a linear combination of a random variable and constant is equal to the sum of the product of n constant and the mathematical expectation of the n number of variables, or e summation aixi equal to summation aie xi, where ai equal to I equal to 1 are constants.
Thank you so much, INDRIM. Now I shall continue the next slides. So the next slides consist of addition theorem on expectations. The first addition theorem on expectation is that statement for discrete random variable. The statement for discrete random variable states that if x and y are two discrete random variables, then x plus y equals to expectation of x plus expectation of y. So here we have the proof of this statement, and here we have an example of addition theorem of expectation. So in this particular example, it says that find the expectation of the sum of the number obtained on throwing two dice. So let us see the solution. Here in the solution it says that let x and y denote the number obtained on the first and the second dice respectively. Then each of them is a random variable which takes the value 1, 2, 3, 4, 5 and 6. Those are the 6 sides of a die with equal probability 1 by 6. Here in this example it says expectation of x equals to summation of xi pi, that equals to 1 into 1 by 6 plus 2 into 1 by 6 up to 6 into 1 by 6. So here we will add the um, here we will add the numerators, that is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by the denominator 6. So here we will get the result 21 by 6, that is 7 by 2. Similarly, the expectation of y is also 7 by 2. So here we have a table for this particular problem. In this table, the values of x are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. And similarly, we have the values of px, that is 1 by 36 for the value of x equals to 2, 2 by 36 for the value of x equals to 3, 3 by 36 for the value of x equals to 4, 4 by 36 for the value of x equals to 5, 5 by 36 for the value of x equals to 6, 6 by 36 for the value of x equals to 7, 5 by 36 again for the value of x equals to 8, 4 by 36 for the value of x equals to 9, 3 by 36 for the value of x equals to 10, 2 by 36 for the value of x equals to 11, and 1 by 36 for the value of x equals to 12. Here we can see that expectation of x plus y equals to 2 into 1 by 36 plus 3 into 2 by 36 up to 12 into 1 by 36. So here we are adding the numerators again, that is 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12 divided by the denominator 36. So we are getting the result 7. So here the expectation of x plus expectation of y equals to 7 by 2 plus 7 by 2, that is equals to 7. Therefore, the expectation of x plus y equals to the expectation of x plus the expectation of y. So now let's continue with the second statement for addition theorem of expectation. So the second statement is the statement for continuous random variable, and it says that let x and y are two continuous random variables with probability density functions fx and fy respectively. Then expectation of x plus y equals to expectation of x plus expectation of y. And we also have the proof for this particular statement here. So up next we have multiplication theorem on expectation. So the first multiplication theorem on expectation is that discrete random variables. The statement states that if x and y are two independent variables, then expectation of x into y equals to expectation of x into expectation of y. And we have the proof for this particular discrete random variable. So let us continue with an example to understand this probability theorem much better. So this example states that two coins are tossed one by one. First throw is considered as x and the second throw is considered as y. Following joint probability distribution is given by getting head is taken as 1, whereas getting tail is taken as 0. As we have seen that these particular variables are independent of each other, that is, we are going to get either head or tail in a toss. And here is a table to understand the probability in a much better way. And here is the solution for the problem. The solution states that a random variable xy can take the values 0 and 1. Here we can see that expectation of x into y equals to summation of x y p x y. That means 1 into 0.25 plus 0 into 0.25 plus 0 into 0.25 plus 0 into 0.25, that will be equal to 0.25. Then expectation of x equals to summation of x pi, that is 1 into 0.5 plus 0 into 0.5, and we will be getting the result of 0.5. And similarly we are going to calculate expectation of y equals to summation of y pj. Here 1 into 0.5 plus 0 into 0.5, it will be resulting in 0.5 is the expectation of y. So then we are going to multiply the expectation of x and the expectation of y. So upon multiplying both the expectations, we will be getting 0.5 into 0.5, it will be equal to 0.25. And here we have verified that expectation of xy equals to expectation of x into expectation of y. Let us now see the continuous random variable. The continuous random variable states that if x and y are independent random variables, then expectation of x into y equals to expectation of x into expectation of y. And here we have also given a proof for this particular statement. With that, we will be concluding our presentation. Thank you very much.